I'm back. This is kind of a part two of the last one in terms of periodic trends. We discussed why the atomic radius is bigger going down and why the atomic radius gets bigger going to the left. Technically, we described why it gets smaller going to the right. That's fine. But now we're going to discuss the other ones. We're going to discuss electron affinity. We're going to discuss ionization energy. And we're also going to discuss let me get a better pen, electronegativity. We'll show the definitions, but the general trend for these would be that going to the right and going up, they get bigger. Now, for electronegativity, we're going to peel off the noble gases because of the definition, but we'll get to that in a second. So first, the definition is a very technical definition. It's got a lot of pieces to it. If we're referring to IB and getting credit, you have to have all these pieces. This is ionization energy. The key word here is energy. Energy is a delta H, and therefore we're referring to that. In thermodynamics, which delta H would be thermodynamics, if you have more, it's going to require more or you get more, either way you want to look at it. So we need to define an amount. In chemistry, the way we define an amount is typically with 1 mole. That is how many electrons need to come off, and that's how many electrons need to come off of how many atoms, and it has to be 1 mole of electrons from 1 mole of gaseous atoms. Ionization energy is not the energy to ionize. Ionization energy is the energy to remove 1 electron, typically from the valence, and typically we're talking about metals, but this is not part of the definition. It's just to remove. So you need a direction of the electron movement, and that would be leaving. And you can't remove electrons from solids and liquids because you can't get inside. Also, in terms of thermodynamics, if you remember about heat curve like this, we know that there's an energy change associated with a phase change. So energy is phase dependent. Therefore, the most easy thing to do is talk about it in terms of a gas. So ionization energy is energy required. By the way, required means it's going to be endothermic to remove 1 mole of electrons from 1 mole of gaseous atoms. So if you're talking about periodic trends, going from left to right, the size of the atom gets smaller. It's because Z effective gets larger. Z effective is the measured attraction. We can go back and discuss why it gets smaller. But overall, the reason why it gets smaller is because there's more attraction, more measurable attraction. And that's because of the lack of added repulsion. So to remove electrons from the atoms on the right side would require a whole lot more energy than to remove electrons from the left side because of the smaller Z effective on the left, the larger one on the right. So as size gets smaller, ionization gets energy, and they're definitely related. Going down a group, we know that the atomic radius gets larger, and therefore the ionization energy will get smaller. When you have one with 2 energy levels and you have one with 3 energy levels, there's a whole lot more electron repulsion, but the main reason is strictly the distance. The distance between the positive and the electron, because the added positive and the added negatives kind of cancel out, and therefore what you're left with is the electron being removed, which will be the valence, is much farther away, less attraction, easier to remove. You kind of want to, when you describe these things, you kind of want to do like a hopscotch thing. This may not make any sense, but you're going to have the electrons are farther away. That means less attraction. Less attraction means easier to remove. Easier to remove means less energy to remove it, and ionization energy decreases. Electron affinity is really similar to ionization energy in the sense that we're talking about 1 mole of electrons, we're talking about 1 mole of atoms, a gaseous state, except in this case, the atom's going to add the electron to become an anion. What kind of things add electrons to be an anion? Non-metals typically. So even though we're talking about periodic trend going from, left side to right side, what we're really talking about are in the non-metal section. Also, going from left to right, you add more protons, you add more electrons, they kind of cancel out. And what happens is that the electron is going to want to stick to this to become negative. We're talking about the first one here. So oxygen will get 2, phosphorus will get 3, but these are energies, and so they do it stepwise because the energy changes. Ionization energy is the same thing, and we'll talk about second ionization and third ones later. So here we're talking about one electron sticking to an atom more on the left side. We have one electron sticking to atom kind of more toward the middle of the nonmetals. And here an electron sticking to, like, I don't know, maybe a halogen. So we can think of this as phosphorus and sulfur and chlorine. Once again, it goes back to proximity. The electron for the chlorine that we picked out, or anything on the right side, will tend to be attached to something that is closer to the nucleus. Proximity of a positive and negative means it's going to be a stronger attraction, and will actually have more energy released. So it's like an absolute value. A larger negative released as the electron is attaching. For the one more toward the middle, you would have farther distance, and therefore the attraction isn't quite as big. And then for phosphorus or something farther to the left, even bigger, so the attraction is even less. So the energy being released is less energy, or a smaller negative value, a smaller absolute value. Last one, this is electronegativity. Electronegativity is an attraction that a shared pair of electron has to the positive nucleus of an atom. Now, this is referring to not just the pair, it's referring to the atom. So chlorine's going to have an electronegativity of a certain value, and hydrogen's going to have an electronegativity of a certain value. And we can compare these values to see who has a greater attraction to the shared pair, which is right here. So these are going to be valence electrons here. Core electrons are not shown, and so we're not referring to any of those. We are definitely referring to this shared pair right here. Now, as you know, going from left to right, the atoms get smaller as they go across the period. As you know, going from top to bottom, the atom gets bigger, going down a group. But what we're looking at is Z effective still, right? Z effective is going to be the attraction to the nucleus, given the attractive forces of the protons and the repulsion of the electrons both. Because if you're attracted by 17 protons but repelled by 16 electrons, the actual measured attraction isn't 17. So if you look at this, the overall trend is fluorine is the biggest. Fluorine is the biggest because we're not counting noble gases. Noble gases typically do not covalently bond. There are always exceptions. The exceptions are farther down, such as in xenon, but they typically don't. So we're just going to strip off that whole group and use the rest of it. If we strip off that whole group for the noble gases, fluorine is the top right. So looking at this structure, we have a chlorine and we have a hydrogen. So if you look at it, it's hard to tell by looking at the table so much. Fluorine's number one for sure. Fluorine's number one right here. And then over here, oxygen is number two. And then down here, chlorine is going to be number three along with nitrogen. They have the same value. They have arbitrary values that you don't have to memorize. But the values, if you looked at a chart, fluorine is a 4, oxygen is a 3.5, chlorine's a 3.0, and so is the nitrogen. So these are values of the attractive force to a shared pair of electrons. We get to this in a later chapter, but because chlorine tends to pull this pair toward it, the electrons will go around, they'll go around, these things are in here, but they spend more time around the chlorine, and so the electron cloud is denser around the chlorine in compared to the hydrogen. So you end up with this vector of an arrow in which the positive looking part is positive and the arrow is negative. We can also do a lowercase d. So it's going to lowercase delta plus, lowercase delta minus, and we'll talk about this in terms of polar bonds. Polar bonds are all based off of differences in electronegativity. And electronegativity is based off the size of the atom going left and right and overall Z effective going up and down. All right, now we're going to talk about subsequent ionization energies. So if you look at this, they have delta H's. This might be I for a subscript saying, oh, it's ionization energy, but also maybe I1, this could be I2, this could be I3, and this bottom one is going to be I4, meaning the fourth electron being removed from the atom, not necessarily from the energy levels, but from the atom. So if you remember what magnesium is sitting right here as an alkaline metal. It's in period 3, but it's in group 2, and it's got 12 protons, which means 12 electrons. For this first one, we can draw plus 12 in the middle. We have 2 electrons in the first energy level. We have 8 in the second one, 5, 6, 7, 8. And in the third one, we're going to have 2 electrons. So that would be magnesium uncharged. So we're going to come in here and we're going to remove 1 electron here, and that's going to remove that one, and it's going to require energy, 740 kilojoules. So that one's gone. So if you think about that being gone, now we're looking at a +1 ion. Well, +1 ion has a greater charge. Now, technically, it doesn't in the middle. It's still a 12, but fewer electrons means less electron repulsion. Okay, less electron repulsion means that the electrons are going to be pulled in tighter, it's smaller, and then it's going to require more energy to remove this guy right here. And it shows in I2 that it requires more energy to remove the second one because of lacking electron repulsion. Now that I1 is complete and I is 2 complete, we have lost that valence electron, so there's no more valence electrons there. So essentially, while the energy levels still exist, we can kind of, it's empty, so we kind of think it doesn't exist in terms of like when we draw it. So now hypothetically, we can remove another one. If we remove another one, this would be from the 2p section, because p's have more energy than s's on any given energy. But for our middle school drawing, it's just the next electron down. So not only is there less electron repulsion from the previous one, you're also removing an electron from energy level 2, or a core electron. Back to one of my statements earlier, if we can state more specific the fact that we're removing not only a core electron, but an electron from the second energy when we were removing it from the third energy level, that is a more precise definition and reason behind it. So you'll notice that when we remove that electron, not only does it require even more energy, it is exponentially more. So if you go from what is 750 to 1400, it's about half as much. What, or you have to go twice as big. And then you go from 1450 to 700, it's like 5 times bigger. And while there's a big jump between the third and the fourth, it's not 5 times bigger. So we're looking at the relative jumps in ionization energy. And for that reason, we can determine that this right here, if we didn't know what the metal was, because of the big jump between the second and third, we would know we have 2 valence electrons and therefore group 2 atom. And again, if you remove yet one more, you're still removing it from a core. You're still so it's still gonna be a very large energy. However, you'll have even less electron repulsion, so the energy amount does increase yet once again. But again, if I give you just a set of ionization energies right here, you can determine what group it's in by looking at the jump in energy values.